So first, I'd like to offer you another podcast. This by Kevin Jones. It kind of emphasizes the point that medicine is not black and white in diagnosis or treatment. And Kevin Jones, a surgeon, he'll give you some examples about things in medicine, not nearly as long as the others we did. Today we're going to talk about measurement. And that's one of the things that you will find often in the literature. I mean, we've used a lot of scales. Some of the scales that have recently come up, the convergence insufficiency symptom scale, Dr. Laukonen's BIVS, the brain injury vision symptom scale. There are a number of scales that we use, and today we want to talk about how you read subjective types of scales. Now, there are other kind of scales like taking your temperature. Those are objective, definite numbers. We're talking about unobservable latent variables. That is, things that are inside, some concept of a feeling, a symptom, what's bad. You can't really objectively measure how bad you feel. You have to ask a question, and then how do you put that into a meaningful metric? So some of our keywords today, they're data types. We have nominal variables. Those are things like blue, red, green, boy, girl, stuff like that. Ordinal, that's your typical Likert scale on a scale from 1 to 5. Do you agree or disagree with something? Interval ratio, that scales like temperature, the eye chart, and the like. Latent variables is a concept. It's, again, this unobservable construct. You never can directly measure a latent variable, but you try and get to it. Likert scales are ordinal scales, and we'll talk about how to measure them. You'll hear a lot of times, since they're rank scales, that you can't take the average or anything like that on that. That's not quite accurate. We're not going to go into detail of when it's appropriate to use them or not. We're just going to say that in appropriate situations, it's perfectly fine to take averages and do other types of analyses. Rasha Analysis makes no assumption of the data. You can, again, have 0-1 type data. Yes, I have this factor or feature or not, or yes, I can do this or I can't. It can also be on a scale from 1 to 5, I can do this or I can't. But they collect their data and analyze it a little differently, using how many people would give certain responses, convert that to ratio level data. So there are many uses of scales. We have eye charts, attitudes, patient satisfaction, competency, life tasks, symptoms. We've talked about the BIVS. There's also dry eye scale, very popular scale. But again, it's getting at those symptoms that you can't really objectively measure, but how do you make it a metric so that you can? And so let's just think of what is the purpose of a scale. Well, it is to locate a person's point or position along one of these underlying unobservable dimensions, the latent variable. So at the bottom of this, you see we have an overall scale, and the blue line represents this dimension. And in this case, good is to the left and bad is to the right. And so we have two people on this scale, and they have a particular position on the scale. And their position is invariant. It is what it is, no matter what the questions are. And we would like to have questions that exactly show where the person is, but it doesn't really work that way. But the blue line is this dimension, this univariate dimension, an underlying scale. And this scale, in this particular example, goes from positive to negative. Now we're first going to talk about Likert scales. It was introduced in 1930s by a guy named Likert. The history of this is pretty interesting when you think about a national survey being conducted before computers. The questions have various types of response scales. One was an ordinal, strongly agree to strongly disagree, and one was never to always. And he was the first person to really consider taking averages before people had done frequencies, how many people respond to a particular response, and converting it to the normal distribution z-scores based on frequencies rather than taking the average. It's okay to use Likert scales when you're combining them into a particular subscale. If you've broken it down into subscales, sometimes you do, sometimes you don't. The dry eye scale is just a single scale. The convergence insufficiency symptom scale is a single dimension scale. The BIVS is considered both ways. As you read in the paper, we did it as a single scale and eliminated a few questions with the Rosh analysis, and we considered it multidimensional, and each of those dimensions had its own question. But the idea is that the items all describe, in a particular subscale, the items all describe a similar subscale, and they're all giving you the answer for a particular spot. The more questions you have for each subscale, the more the mean of the questions accurately identifies the location. So here, let's take an example. So remember the bar at the bottom is kind of the average overlying scale from positive to negative. And the little guy on the right, he has this fixed location underneath. And each question is getting at this same underlying dimension. But the actual questions can vary in their points on where they measure. So if you enter, for question 1, if you enter a 1, you're a little above the happy guy. A 2, still. 3 below, 4 and 5. And for the sad guy, all questions are above him. So what you do is, for the happy guy, you take the closest. The average is going to give you the person is likely to say 2. So for the happy guy, so the person would respond 2 because that's the closest the person is to that dimension. For the sad face, he would give a 5 because that's the closest item on this scale. Even though it's not right at the 5, it's the closest. And you can see in question 2, 5 is a lot closer and on the other side. On question 3, the sad guy would pick number 4. So you'd have 2 5s and a 4, and you'd have a total score of 14 over 3 or 4.67. Whereas the happy guy, he goes 2 and then he picks a 1 because he's above all the questions, and then a 2. So you have 2 plus 1 plus 2 is 5 divided by 3. He gets an average score of 1.67. And the average comes closer to the true point on the dimension than any one question by itself. Now let's talk about Rosh scales. And these are, Likert scales tend to be more towards feelings and attitudes, and Rosh tends to go more towards competency. But again, it's not ordinal. So if you're blind, you can't see it all. Well, if you're completely blind, you can't see it all. You're a little better if you can see to walk. You're even better if you can see to drive. You can even better to read a newspaper, and better still to thread a needle. There is an order to these based on competency, and the scale seeks to find a single point along an unobservable dimension. So if you can drive, then you can probably do tasks below that you can do, say walk, you can walk. But if you can't read a newspaper, but you can drive, then that's where you are. But if you can read a newspaper, but not thread a needle, then you're kind of at that point in the order. But generally, if you can read a newspaper, you can drive and walk. And if you can thread a needle, you can do all those below it. Similarly, if we think of another example of visual competency, we can look at a Snellen chart. Now, the Snellen chart does actually have the a objective way of looking at this, but we can kind of think of it as a single dimension of visual competency. So if you can't see the big E, you're not going to be able to see the FP, TOZ, and so forth. But if you get down to the EDF CZP line, then you can see everybody above that, the bigger letters above that. But if you miss the FEL, you will come and miss all the ones below that. So there's some point along this dimension, this single unidimensional scale that gives you a point that you can do. If you think about it, each letter is a question, and the questions are rank ordered. Starting from the top, you can correctly answer questions until you hit the limit of your visual competency. So the underlying scale single, letters like L, P, E, D are all measuring the same thing, so they're kind of redundant, and so forth. So as I said, Rasha analysis, just like the Likert, is finding a single point on a single dimension. Now, one thing that the Rasha analysis does is when we look at these dimensions from the Likert point of view, it just talks about items. The Rasha analysis actually does both. It puts a person on a dimension. So there are some people more competent than others, as well as scores on this dimension. And they all kind of do that. The Likert does also, but the Rosh analysis does it in a more formal mathematical way. We're not going to go into it. Unlike the Likert scale, the data is not based on an average score, but the proportion of people who are competent with a particular question. So the easier the question, the more people who can answer yes. Can you see a walk versus can you thread a needle? So more people can walk than can thread a needle. And just for your information, not that we're going to go into it, but you actually look at what's called a logit, and that's the natural log of the proportion of people that can answer the question correctly divided by the proportion of people who can't. And the logit has a range from negative infinity to positive infinity with a mean of 0. This procedure turns any question, even though it's ordinal in nature, into an interval data based on this logit. The logit is interval data. So just to summarize between the two types of measurement scales, the Likert scales are best for symptoms, feelings, or attitudes. And the Rosh analysis is best for measuring levels of competency. The underlying observable scale is one-dimensional in both cases. They're both non-observable dimensions that are subjective scales trying to come to and create an objective measure. The response in the Likert scale, each question covers the range of the underlying scale. In Rosh analysis, each response represents a point along the scale. In Likert analysis, the response to each question represents the person's location on the underlying scale, and Rosh analysis similar, but you can kind of think that at the point where a person on this scale misses a question 50% of the time, that's where that person is located on the scale. Where 50% of the people will, well, no, 50% of the person. The appropriate summary statistic for a Likert scale is the mean or median, but a sum can also be used. A sum is used in the CISS, and it's usually 16. Above 16, people consider you to be symptomatic. On the Rasha Analysis, items are ranked in order of difficulty. And though it's not completely true, questions, the assumption is that on this scale, questions below are a particular point are easier, questions above a particular point are harder, but it doesn't mean that you, like the I scale, it's going to be perfect. There's a lot of error in these questions too. So I asked you to review the BIVs, and basically that was a study where we compared first-year optometry students, third-year and the first years were taken right after they signed on, started optometry school. Like, if it wasn't orientation, it was pretty close. And they completed the scale. And then the third years were given the same scale, not the same students, but the same optometry students were given it a week before board exams. And then there were TBI patients. And when we submitted this paper for review, there was some concern of the differences in ages between TBI and our optometry students. So we have a fourth category where we split out those patients who were in the age range of our optometry students. And so in this case, we did what's called a factor analysis because remember we talked about a single underlying dimension. It looked to us like there were 8 different dimensions. And some of these dimensions tend to be a little correlated with each other, but others, but it still came out to these factors. And so the question, so for example, you can look at the first dimension, that's reading difficulty, slowness with reading and writing. And a 0 was well, these are factor z-scores. So look at these numbers and think in terms of the mean minus the standard deviation, or the mean, the score on a particular, the average score for the particular subscale minus for an individual minus the mean of all individuals for that subscale divided by the standard deviation. That's a z-score. By using z-scores, we can directly compare the degree of severity, I guess you would say, of each of these. And we use the first years as kind of the standard, and we compare everybody against them. So the means of the means of the first years were used, and then you can so the first column of each, there's 4 sets of columns for each subscale. The first is the first years, the second is the third years, the third is the TBI patients, and the fourth little bar represents the age, similar age range as the optometry students. And you can see pretty much across the board that the TBI patients and the age restrictions were all pretty similar. The other thing that you can see is at least on 6 out of 8 of these subscales, the TBI patients are a lot higher. And so remember we said you were clinically relevant at 0.5 standard deviations. Well, you can see that 6 out of 8 of the TBI patients in both groups were at least 1 standard deviation greater than the first year optometry students. And for peripheral vision, the one on the right, what looks straight ahead, isn't always straight ahead, that kind of a question. That was the top question in that factor. There were a couple others. You can see that they were between 5 and 6 standard deviations out. So peripheral vision was a big one in discriminating between TBI and optometry students. Now notice that in the middle there we have dry eyes. My eyes feel dry and stinging was the top question, the most heavily loaded to that factor, and double vision, especially when tired, was another one. And you can see that actually the third years are substantially greater score, had higher scores, more towards the end of the scale than the TBI patients, and even the first years. Non-overlapping error bars, or error bars have been constructed. They're not confidence intervals, and they're not standard errors. They're constructed so that if they don't overlap, they're also significantly different. So not only do you get the effect size, but you get a sense of the p-values, because if they're not overlapping, they're significantly different. So that's how we would read this, and it's multidimensional, and you can give your patient this scale and you can get a profile and see under which dimensions are higher. And there are probably different categories. We haven't done this yet, but that's one of our future things. Are there types of TBI patients that can be determined by the shape of their profile? So it might, probably most will have this peripheral vision, but some might have others that are higher and lower depending on the nature of their injury. We want to look into that for sure. Okay, here is the BIVs with a Rasha analysis. Now, what we have here is what's called a bubble plot, and the questions are rank ordered by symptom, degree of symptom. And so, for example, the question that is most discriminating is at the top of the scale, and that's question 22, what looks straight ahead isn't always straight ahead, and that, of course, is the question at the right that had the highest on the Likert scale. Now, it's kind of interesting about this because the assumption to do a Rasha analysis is that there is a single dimension. And we said there were 8 dimensions here. So is it legit to do a Rasha analysis? Well, that's kind of a good question. And so the Rosh people have a guideline on how correlated these subscales can be before it's too much off to be considered not a single dimension. And we actually were within the guidelines for calling it a single dimension. Although you can see that while if it was a perfect scale, all these little bubbles would fall on this line that's going straight up the middle here. And you can see they deviate, some deviate more than others. And here's the dry eye question. You can see it's fallen off to the right. And that is not a good question to discriminate between TBI. And in fact, in the total score, we don't use that because, as we've seen up here, dry eye is good for third years, but not discriminating for TBI people. The double vision one isn't very good either. So the second one, the second hardest or the second most discriminating question for TBI is also a peripheral vision one, side vision, distorted objects move or change positions. So again, if you're not a single unitary dimension, you're going to fall a little bit off this central line, and this is wiggling around a little bit, but it wasn't bad enough to not call it a single dimension. And Dr. Laukkanen wanted to have 2 ways of doing this study. One with the profile that lets you identify different types of TBI, but he also wanted a quick test for that a technician could run and just to identify people with symptoms. Now, that brings me to the point that you will, throughout your career here, have your faculty telling you that you use this to help diagnose either TBI or, in the case of the CIS, convergence insufficiency syndrome. And if you are above the criteria, you're outside what a normal person without those conditions would have as a score. But it doesn't really guarantee that you have a TBI or a convergence insufficiency. Accommodative insufficiency can also be out a score greater than 16. So the CISS can't tell the difference between accommodative and convergence insufficiency. So, but it is one tool that tells you, okay, this person has symptoms. We should look further into what the problem is. But it doesn't absolutely define a brain injury or a convergence insufficiency. Now, something that is near and dear to your hearts is the analysis of the midterm. So these are the 30 questions on the midterm. And actually, they are very close to a single underlying unitary dimension. Question 29 is getting off the mark a little bit, but none of these questions were outside the standard criteria for a quality question. Now, one of the things that was interesting, and we're going to talk about this at the end of the class, but the two best questions, or not best, but most discriminating questions were question 22 and 27. And a lot of people missed those two questions. And in fact, so many people missed them that I gave everybody credit for them. But I do want to say that actually they were very good questions, because the people that got these questions correct did very well on the exam. And people who missed them did poorer. And so the first question I eliminated, even though it was a high quality question. I got rid of it because it was pretty wordy. And I think there was I was trying to get at, I was visualizing a picture and trying to put it into words. And I think my expectation was, I didn't meet my own expectations in the description of this one. The second one is actually the definition of a p-value. And a lot of people missed this question. And so I am concerned that we missed this one so much, because this is one of the fundamental principles that I want you to get. So we're gonna cover what it is, and you will definitely see it again on the final. And then down here was the easiest question, and that was the effect size. So basically, you guys were able to plug and chug pretty well, but getting at what the numbers meant was a little more challenging. So we're going to cover that in a moment. So here we give this is the distribution of scores in the class. The lowest score was 21, the highest score was 30 out of 30. And this graph down below shows the distribution of Rosh scores, and on the same identical scale, the distribution of the item analysis. Now, generally speaking, if you're doing a BIVS or a CISS, you would want these two types you would want the items to completely overlap the people. In a midterm, not so much, because what that means is the midpoint, you want to say that 50% of the people missed half the items. And so rather than failing at 75%, 50% of the people would get a score above this midpoint. So that's not in a midterm. You really want the people to be piling up at the end of the scale. You don't want it to be too far up here. If all these blue points were way up here and the items were down here, the test would be too easy. And if all the blues were down here and the red were up here, the test would be too hard. So we want it to be just right, and actually you guys did as a group pretty well. You can see up here that the 22.5 is the 75th percentile. So for these folks down here, homework is very important because homework can bring up your score. So you can fail the midterm but still be okay if you've done well on the homework. That's the idea. So but here people actually did pretty well on the midterm for the most part, and you can tell how this distribution is like that. I might just add that the OATs use Rasha Analysis, and the scores on the Rasha Analysis are recalibrated so that the distribution, so they do it with a frequency. So your raw scores, when you see a 300, numbers have been moved around so that the distribution is normally distributed. 68% of the optometry student applicants fall between plus and minus 1 standard deviation, with the mean being 300. And 95% fall within 220 and 380. So you can kind of get an idea where you are on the various subscales within that. So the OATS has a number of subscales, like they have one for physics and etc. And then they have a science is another subscale made up of subscales. But and they're all separately recalibrated, by the way. So you don't take the average of the science subscales. You take the overall science scores and you recalibrate it to that. When you have a spread, that's called separation. They try and get good separation where there are easy questions versus hard questions, and they try and get separation on the people so that there are people that do poorly and people that do well, and get good separation and throw out questions that don't fit on that single underlying dimension like science or physics. So what have we covered today? We've covered Likert scales used to measure attitudes and feelings. We've talked about Rosh analysis used to develop competency scales. Both types of analysis have the assumption that there is one underlying linear scale. Some scales, like the BIVs, consist of multiple single-dimension scales. You'll notice we did not do anything about anything that you have to compute. There's no computations involved with today's discussions. It's more about the concept of what these scales are representing. These are behavioral scales that they're trying to get at this underlying latent subjective types of things and how to convert those into a metric where you can fairly compare different individuals or the change of an individual's behavior over time. All right. So I think that we kind of had a problem on two of these. And I want to make sure that you get this concept, because especially the p-value. Many people have an idea in their head about the p-value, and I have tried to convey that what this is, and I think I haven't quite gotten it across yet, so I'd like to spend a little bit more time on it. Remember, we said hypothesis testing is a two-stage process. First, eliminate chance, and then determine effect size. So at first, we're talking about eliminating chance. But let's step back a minute, and let's consider two distributions. We have over here a distribution of observations. And let's think of it in terms of our IOPs. So 95% of people without glaucoma fall between the mean, which is an IOP of 15, and two standard deviations, which is 2 times 3.5, or 7. So between 22 and 8. If you are a 22 or above, you are considered an outlier. We have rejected you as having a normal IOP. It doesn't mean you're not normal, because there is a few people out here. But for practical purposes, it's never 100%. I mean, this curve looks like it hit 0 here, but it really hit 0 closer to plus and minus 5 standard deviations. So it's a lot bigger. Very low probability. The further out that you get, the probability gets smaller and smaller. But at 2, your probability of being normal, about 2.5% of the people fall out in this direction, about 2.5% fall out in that way, and that's if the distribution is normal. But you're an outlier. That's the point here. You're an outlier to normal, and we would say that if your IOP was greater, 22 or greater, we would want to do some sort of further testing and keep an eye on it and see what's going on with your pressures. Not necessarily do anything about it, but track it. Now over here, we have a distribution that looks just like this one. Only here, it's a hypothetical distribution of means. And that's what makes this whole thing kind of confusing. Because when we talk about t-tests and statistical tests and the like in the standard error, this is the standard error squared, standard deviation divided by the square root of n. And same way here. It's the sum of two different means. So we're looking at the difference between means. Maybe we look at a person before a person with high IOP before they start taking drops, and then a couple months later, after they've been taking them for a while, and see if the drops work. And so we have a mean of people at 2 different times, and we have a bunch of people in this little study that we do. And then we look, and instead of a z-score, which is the mean minus the or the observation minus the mean over the standard deviation, we have a t-score, the difference in means, which is a single number, a difference, divided by the standard error of the difference. Now, remember, a standard error is just a standard deviation of a sampling distribution of means. And this particular distribution that we're talking about is the null hypothesis. Because the only thing we know from statistical theory, we know that if you sample n people from each group, and you're going to rarely get 0, even though 0 is the truth. There's going to be random variation. And it's going to bounce around here, and based on the standard error, it's going to also be smaller if the sample size is big. It's going to be bigger if the sample size is small. It's the same standard deviation. It just the width of this distribution just changes as a function of sample size. But from statistical theory, we know that if the difference is 0 and there's random variation, the normal distribution is going to tell us exactly what the t-value will be when we're plus or minus 2 standard error of the differences out. And if this difference is big enough that you're an outlier, we say you're statistically significant. So this value, this p-value, this small p-value, because you have little probability of being an outlier, is the statistic. If you got a statistic, a t, out here, that's the probability of finding this a difference this big if the null hypothesis is true. It doesn't really say if it's an important difference. That's the key thing. That's what everybody confuses. I think if you're out here, it's important. But remember in our SVL, PAL groups, we had this really skinny, tiny standard error, which is if we had only run 30 or 50 subjects in each group, the t-value would have fallen well within the 95% range, and there would have been no statistical difference. But when we say we rule out chance, we mean an outlier rules out the probability that it's chance. Now, again, it could be wrong, but generally speaking, we're willing to take this little risk to rule out chance, and then we look to see how big our effect is. Not by this number, but by the same mean difference divided by now the average standard deviation rather than the average standard error. We don't call it a t, we call it an effect size. So this is what we need to know that people are kind of getting. All right, hope that makes a little more sense now that you've thought about it and studied it, and just clarify it. Now, the other question, I mean, that was just confusing. I was hoping that my thought was I had this graph that I presented before in my head, and I talked about these are observations of one group to another. And you can see that the orange line down here is the mean of the orange group, but all these people under blue are doing just as well as half of these orange people. And this blue line is the mean of all these blue observations, and almost half of the oranges are doing just as the same as the blue. So the observations are massively overlapping with an effect size of just 0.22. And that was kind of the point of that question. So the take-home message here is observations will overlap, but effect size of 0.22 is really close. 0.5 is pretty close too. If you think about it, when we talk about an individual person, like we did up here, you had to be 2 standard deviations out. When we're talking about effect size of 0.22, that's only 0.22 standard deviations out. Or 0.5 we're calling clinically relevant. That's a long ways from talking about that, but it's talking about means. But individuals can be way, way out here. So you just have to keep it in your head that you're either talking about means or you're talking about observations. They are very different. Means are always closer together than the observations. After recording this lecture, I thought that the concept on this slide may not have been very clear. So it's a snow day, I'm recording it again. I'm going to add just one more slide just to kind of emphasize this last point a little bit. So on the left, we have an effect size of 0.22, and the observations really overlap. Over here, the effect size is 1.8, the same as the height between men and women optometry student. And you can see that here is the mean of, let's say, the women, and the males only overlap a little bit. And over here, this is the mean of the males, and you can see the women only overlap a little bit. As to over here, the overlap is great, but in both cases, the p-value is less than 0.05. This was, I think, 0.002, and this was 0.004. So both groups are highly significant. And one of the differences over here, we just had a really big sample size. And so that makes these little error bars very narrow, so that you can get statistical significance on a trivial difference. Over here, the bars are much wider, but they're still pretty far apart because the effect size is so big. So I just want to get the point across that observations are different from means, and you need to use the effect size to get an idea on how different these groups are in terms of standard deviations. With a t-test, you get the difference in terms of standard errors, but that's subject to sample size, so it's a big difference between the two. I hope this clarifies it, and we can talk more about it next week if you have any questions, or you can always send me an email and stop by my office. All right, homework. Read AOA clinical practice guidelines on the care of patients with diabetes. Next week, we'll have another lecture. Thank you.